Now let's take a look at calculations for examples of parametric curves. Starting with finding the length of the curve where x is given by t cubed, y is given by t squared, and t is restricted to the closed interval from 0 to 4. Notice that on that interval both x and y are one-to-one functions, and therefore the curve is traversed exactly once as t increases from 0 to 4. X and y are both polynomial functions of t, and therefore we have a smooth curve. So we apply the formula, and L is the integral from 0 to 4 of the the square root of the sum of the squares of the derivatives of x and y. Derivative of x is 3t squared, derivative of y is 2t. So we obtain 9t to the fourth plus 4t squared inside the square root. And factoring t squared, we get the square root of t squared multiplied by 9t squared plus 4. So now I have the square root of t squared multiplied by something. I can pull out this t squared and I get square root of t squared, which is absolute value of t. But since I'm on interval for t where t is positive, I get just t. So we get the integral from 0 to 4 of t multiplied by the square root of 9t squared plus 4. Well, you see that what we have outside is a constant multiple of the derivative of the function inside the square root. So a natural way to calculate this integral is to use a substitution. U is 9t squared plus 4. When we calculate du, we get 18t dt. So I can replace t dt by 1/18 of du, and therefore this integral rewrites as 1/18 integral of root of u du. And you see that we have changed the bounds of integration. That's because in the first integral we have integral against a variable t, and the bounds of integration tell us the range of values that the variable t takes from 0 to 4. In the second integral, where we integrate against the variable u, we have to specify the range of values that u take. And if t is 0, then u is 4. That's how we obtain the lower bound of integration. While if t is 4, then u is 9 times 16 plus 4, which is 148. To calculate this, we can use the fundamental theorem of calculus, because it's easy to get an antiderivative of square root of u. Square root of u is u to the 1/2. So using the power rule for antiderivatives, an antiderivative is u to the 3/2 over 3/2, so that is 2/3 of u to the 3/2, and therefore we get 1/18 multiplied by 2/3, and then we evaluate u to the 3/2 between 148 and 4. The product of two fractions in front simplifies as 1 over 27, because 2 over 18 is 9, and 9 times 3 is 27. And then we have 148 to the 3/2, and then minus 4 to the 3/2, which is 8. So to look at a second example, let's try to find the length of the asteroid of parametric equation x of theta is 4 cosine cube of theta, and y of theta is 4 sine cube of theta. And even though it's not written here, this is a curve that we have studied before in a previous video, and of course you may want to refer to that. When we studied it, we've seen that to traverse this curve exactly once, here we would have to restrict theta to an interval of length 2 pi, for instance from 0 to 2 pi. And we had seen at that time that this curve has two axes of symmetry, the x-axis and the y-axis, and using this symmetry we could restrict ourselves to study the curve on the interval for theta, going from 0 to pi over 2. And as we do that, here is a point corresponding to theta equal 0, and as theta increases from 0 to pi over 2, we describe exactly once, traverse exactly once this portion of the curve, 1/4 of the curve, and we obtain the rest of the curve by using the symmetry with respect to the y-axis and with respect to the x-axis. So of course, because of this symmetry, we only need to find the length of the curve on that interval and then multiply by 4, because the other the rest of the curve is obtained by symmetry, and 4 times this part gives us a total length. So the length is 4 times the length of this portion of the curve corresponding to the parameter theta ranging from 0 to pi over 2. That means 4 times the integral from 0 to pi over 2 of the square root of the sum of the squares of the derivatives. And if we calculate the sum of the squares of the derivative of x is 4 times 3 times cosine square theta times the derivative of cosine theta, which is negative sine theta. So we get negative 12 cosine square theta sine theta. As for the derivative of y, we get 4 times 3 sine square theta times the derivative of sine theta, which is cosine theta. So we get 12 sine square theta cosine square theta. So if we square what is in each one of the parentheses, we get square of 12 is 144, and then cosine to the fourth of theta multiplied by sine square theta for the first parenthesis, and then sine theta to the fourth times cosine square theta for the second parenthesis. And now you see that we can factor out the common factor cosine square theta sine square theta, and this is multiplied in the first term by cosine square and the second term by sine square. So we obtain this, and of course what we have in the parenthesis on the right hand side now is just 1. So we obtain 144 cosine square theta multiplied by sine square theta. And this is a quantity that we're going to plug inside the square root in our formula for L. And square root of that is of course 12 cosine theta sine theta. Well, formally it should be 12 absolute value of cosine theta, absolute value of sine theta, but since we restricted ourselves to the interval from 0 to pi over 2, both cosine and sine are positive, and so we obtain 4 times the integral from 0 to pi over 2 of 12 cosine theta sine theta. Using the change of variable u equals sine theta, you see that cosine theta d theta is just du, and so we obtain 48 integral of u du, pulling out of course a 12, which multiplied by 4 gives me 48. And then we changed again the bounds of integration, because when theta is 0, then u is sine of the 0, which is 0, and when theta is pi over 2, then u is sine of pi over 2, which is 1. An antiderivative of u is of course u squared over 2, which takes the value 1/2 at 1 and 0 at 0, so we get 48 times 1/2, 24. So now turn to the next video, where we're going to look at one more thing that we obtained from parametric curves, and specifically we're going to look at the area of a surface of revolution generated by rotating a parametric curve around an axis.